Okay, Cap BC, Unit 3, Day 14, extra review worksheet. Just if you want a little more review. These are the answers. I don't have the work here. I'll show you the work in a little bit. But check the answers, pause the video if you need to. Probably already post them online too. There's the answers to the next couple problems. Pause it if you need to. Here's the answers to 6, 7, and 8. Pause it if you need to. And 7, 8, 9. Okay. So let's see. Okay, we're trying to sketch these without a calculator, so we've got to get the Cartesian equation, set up table, initial terminal points, I want to label the graph, on direction, name the shape it is, whatever. So t equals x over 2, so y equals 4 times parentheses x over 2 minus 2, so y equals 2x minus 2. That's the equation of a line, but because of the time requirements, it's going to be a line segment, piece of a line. So I'm going to make a table. 0, 6, might calculate something in between, maybe 0, -2, 12. That's going to be 22. I mean, that's a big number. So I guess we could try and make our graph really tall. Maybe go by like maybe go by like 2s here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So 0, -2 is right here. 12, 22. Oh, no. I messed up, I think. No, that looks right. 12, 22. So let's count this 2, 4, 6, 8, 10, 12. So 12, 22 would be there. So it's kind of messy. So there it is. 12, 22. It's your terminal point. And 0, -2 is your initial point. Direction is going that way. So there you go. All right, next one. Probably got to use those trig identities. Sine squared plus cosine squared equals 1. Divide everything by sine, you get 1 plus cotangent squared equals cosecant squared. Divide everything by cosine, you get tangent squared plus 1 equals secant squared. So for this one, we use the sine squared one. So sine is x over 3 squared. Cosine is y over -2 squared equals 1. So it's going to be x squared over 9 plus y squared over 4 equals 1. That's a Cartesian equation. It's an ellipse. We make a table. 0 to 3 pi over 2. Plug 0 in, 0, -2. Plug 3 power of 2 in, you get 3, 0. And sketch this graph. So it's bigger in the x direction than the y. Draw a rectangle, lightly, and just sketch it inside of it. We don't know if it's the whole thing yet. So 0, -2 is right here. That's the initial point. Label it. And 3, 0 is over here. That's the terminal point. Oh, wait. Did I do that right? Oh, it should be -3, 0. Now, which way does it go? Does it go around this way? Does it go this way? Easiest way to find out is just plug another value in. Pi is nice. It's going to be 0, +2. So definitely goes up there. So it starts here and goes around the long way. Darken that in. Draw an arrow to show the direction. There you go. Okay, number 3. Tangent is x squared plus 1. Secant is y over -2 squared. So I want the 1 to be positive, so I'm going to leave that there. So it's going to be y squared over 4 minus x squared. So y squared over 4 minus x squared over 1 equals 1. That's a hyperbola. Make table. Pi over 2 to pi. So let's see. Tangent is sine over cosine. So sine of pi over 2 is 1 over 0 is infinity of some kind. And secant is 1 over cosine. So that's also going to be division by 0. -2 over 0. So that's going to be infinity of some kind. So it's undefined, but it's probably on those slanted asymptotes. If you plug pi in, sine of pi is 0, cosine of pi is -1, so 0 over -1 is 0. Cosine is -1, so we get +2. Now we could graph this. It's hyperbola. Up for 1, 2, 3, 4. Down for 1, 2, 3, 4. Right 1. Left 1. Draw a box. Connect the corners. Diagonals. Straight lines. Use a ruler if you need to. It's going to be up, down, because the y's are positive. So 0, 2, that doesn't make sense. That's not the graph. Oh, shoot. It's supposed to just go up to 2. See, got my mistake. So this is what it should be. It's supposed to be the square root of the number underneath it. It's one of the nice things about the table. Okay, 0, 2 is right here. And that's the terminal point. So this infinity stuff could be at like, could be at there's 4 different places where the graph blows up, goes out to infinity. So we could plug another number in. You say, well, it's the same thing as 2 pi over 2, which is like 4 pi over 4, and this is 2 pi over 4, so 3 pi over 4 would be definitely between those. And tangent, that's just going to be -1 because it's the second quadrant. Sine's positive, cosine's negative. And then secant, that's going to be -2 over √2 over 2, which is actually the same as 1 over √2. So it's going to be -2 √2, which is about square root of 8. It's probably about 1.7 or something, or sorry, 2.8 or something like that. So -1, -2.8 is like right here. So I think this is chunk of the curve that we're getting. Shoot. Sorry. -1. This is a question, so it's going to be negative. This should be positive. So it's actually up here. And put an arrow on the end. I don't know why I drew it there. And it's coming in this direction, though. So the arrow doesn't indicate direction there. That's part of the graph. That just means it keeps going, which you need to have. This separate arrow that's just next to it, that shows you direction. So that's terminal point. There is no initial point. And I made a mess of that. Okay. Give parametric forms of these conics. Can you create the parametric equations backwards? So you're being given like information about the Cartesian equation. So circle is going to be x squared plus y squared equals 25, right? I mean, that would be the Cartesian equation. So then you want to think, well, probably going to have the 25s over here because it's going to be one of those Pythagorean identities where it's equal to 1, right? Sine squared plus cosine squared. So we could put, the sine squared here and the cosine squared here equal to 1. So it means that sine would have to equal x over 25, and cosine would have to equal y over 5, so over 5. And this is one way you could do it. And so then x equals 5 sine t, and y equals 5 cosine t. And you also need to give the limits on t. It would take 0 to 2 pi to graph the whole circle. So like that. There are some other ways you could do it, but this is one way. A line segment, we've done these a few times. So this is times 0. This is time 2. These are the x or y values. And so we know there's going to be two equations. One for x, it's going to be like some number times t plus some number. And y is going to be some other number times t plus some other number. So this is our generic equations here. So if we plug 0 in, we get a times 0 plus b equals 2. And so b equals 2. And then we do y 0 equals c times 0 plus d should equal 5. And so d equals 5. And then we do x at time 2 equals a times 2 plus 2 for the b should add up to 7. And so then a equals 2a equals 5. So then a equals 5 halves. And x at 2 equals c times 2 plus d, which we figured out was 5, and that should give you -8. So then that's going to be 2c equals -13, and c equals -13 halves. So then our equations are going to be x t equals 5 halves t plus 2, and yt equals -13 halves t plus 5. And then the time requirements should be part of it. Okay, there you go. So, next part, we're just calculating some different things for parametrics: slope of the curve, vertical tangents, concavity. So, slope of the curve, part A, dy dx equals dy dt over dx dt. So dy dt equals 2, dx dt equals 2t. So we get 1 over t for dy dx. Part B says figure out when it has a vertical tangent. So vertical tangent is when the graph is moving completely up and down. So that's going to be when dy dx is infinitely steep, undefined, which is going to come from dx dt in the denominator equaling 0. So dx dt was 2t. We said it equal to 0. And so t equals 0. Now, I guess we could check and make sure that dy dt doesn't equal 0 there also. So dy dt actually equals 2 all the time, never equals 0, so we're safe. C, we're looking for the second derivative. Now, the second derivative, the concavity, just to refresh your memory, which I feel like this is a good skill, because trying to memorize this equation is too hard, I think. So we're trying to take the derivative of the first derivative, which is a very normal thing. The problem is that this is in terms of t. So we can't take the derivative of something in terms of t with respect to x right away. We could take the derivative with respect to t, like implicit, like if it had y's and y squared, we want to take the derivative of y squared, we'd say, well, 2y, but then we'd follow it up with a dy dx. Same idea here. We take the derivative with respect to t, and then we got to follow it up with the derivative of t with respect to x, the thing we want eventually. So then we kind of write it in this slightly modified, put the dx dt on the bottom. The dt over dx becomes this. So this is the second derivative. And I think you could hopefully get away with not memorizing it. I tried to memorize it for years, and then I figured this out. I'm like, it's not that bad. It makes sense. So we need to take the derivative of dy dx with respect to x, and we already have that right there. So it's going to be negative 1 over t squared, and then we got to divide by dx dt, which was 2t. So it's going to be negative 1 over 2t cubed is the second derivative, is the concavity. Okay, there you go. Number 7, doing the same kind of stuff. Dy dx equals dy dt, dx dt. Dy dt is 2t minus 6, dx dt is 1. So we get 2t minus 6 is dy dx. And B, vertical tangent, it's going to be when dy dx is undefined because it's infinitely steep up and down, which is going to happen when dx dt equals 0, because that's what that comes from. Dy dx is dy dt over dx dt, right? So if you're dividing by 0, that means dx dt is 0. So dx dt equals 1. I'm going to set it equal to 0, which never happens. So the answer is none. And that's the work to back it up. C, we're going to do the second derivative. So we want to take the derivative of dy dx with respect to t first, because that's what we have it in terms of, and then divide it by dx dt. So derivative of that, dy dx with respect to t is 2. Dx dt was 1. So the concavity is always 2 no matter what time it is. So it's a constant concavity, probably like a circle or something like that. Okay. All right, number 8. So A, we're going to do dy dx, which is dy dt over dx dt. I find it helpful to just show the setup. Helps it stick in my head real good too. Just write it every time I use it. So this is going to be negative 2 sine t over 2 or 1 plus 2 cosine t. And then I guess that's it for dy dx. And part B is vertical tangent, which is going to happen when dy dx is undefined. More specifically, dx dt equals 0. So dx dt is 2 cosine t, and we're going to say equals 0. So cosine t equals 0, so t equals pi over 2 plus pi k. So t equals pi over 2, 3 pi over 2, 5 pi over 2 is too far. Now the thing we got to watch out for is double check that dy dt doesn't equal it at the same time. And I checked that here. I didn't check it here because we got none. So dy dt was, oh, sorry, I messed up. This is supposed to be 1 plus 2 cosine t. So this is actually negative 1/2. This is a little different. Alpha equals pi, it's pi over 6, pi over 4, pi over 3. And it's quadrants 2 and 3 that are negative. So t equals, quadrant 2 is going to be pi minus pi over 3. So 2 pi over 3 plus 2 pi k. And quadrant 3 is going to be pi plus that. So it's going to be 4 pi over 3 plus 2 pi k. So the answers are going to be 2 pi over 3 and 4 pi over 3. Now, like I said, I want to check and make sure that dy dt doesn't equal 0 at those places. If it does, I got to do extra work. So dy dt equals negative sine t equal to 0. That's going to happen when sine t is equal to 0, which is going to happen at 0 plus pi k, which is going to happen at 0 pi and 2 pi. None of these points are the same as those, so that's good. And then part C, I guess I'll do over here, is the second derivative, concavity. So I'm going to take the derivative of dy dx, which is going to be quotient. It's going to get messy. Okay, let's try it. Low d high minus high d low all over low squared. Then we're going to divide by dx dt, which is 1 plus 2 cosine t also. So we're going to get, let's try and simplify the bottom. I'm going to combine those together, leave those factored. But the top, I want to try and clean that up. So we get negative 2 cosine t minus 4 cosine squared t minus 4 sine squared t all over 1 plus 2 cosine t cubed now. Now here, I think we could factor negative 4 out of those. Then you have cosine squared plus sine squared, which is 1. So your best final answer here is -2 cosine t minus 4. This bit of work, but there we go. Okay. Number 9, for what values of t is the graph concave up? So that means the second derivative is positive. So we might do a line check or something, but we've got to find the second derivative first. So remember the second derivative, which we were just doing. It's going to be the derivative of dy dx with respect to time, or dx dt. So I guess we could find dy dx first. Dy dx is 8t over 2t minus 4. So this is looking like a quotient rule again. So low d high minus high d low all over low squared. And then we're going to divide by dx dt, which is 2t minus 4. So that's going to equal 16t minus 32 minus 16t all over 2t minus 4 cubed. Those are going to cancel, so it's going to be negative 32, 2t minus 4 cubed. So this is the second derivative expression for all points in time. Okay. We could simplify it a little more. We could take a 2 out. Now the 2 is going to get cubed. So it's going to be 8. Just going to reduce with that. So we could write it a little nicer. Could make our next work easier. So it's going to be negative 4 over t minus 4 cubed. Okay, so we want to figure out, well, where is this e? Actually, should be a 2 here because I factored the 2 out. We want to know, well, where is this equal to 0 undefined? That's going to be at t equals 2. So we do a line check on the second derivative. Test the value, x equals 3. Positive, it's going to be negative, positive, concave up, concave down. We want to know where's the concave up. Well, that's right here. So that'd be negative infinity to 2. Or if we're dealing with no negative time, which we often do on these problems, so that would make sense as a possible answer, would be 0 to 2. Now, we're not going to include 2 because there is no concavity at 2. You can't say it's concave up 2. But you can include 0 because 0, plug 0 in, it's positive. So it's 94 over negative 8, so it's positive. There you go, concave up. I'm going to go ahead and do this other problem, which I gave you guys potentially as another practice. And it's a free response problem. You can find my answers to it. All right, this one, it's got some good stuff in it. I'm thinking it's no calculator. I mean, it doesn't say anything about calculator. We'll see if we can get some answers on these. So, particle moves the xy plane. Here's your time limits. So this actually goes in negative time, which is weird. And here's your x and y positions. Sketch path of the particle in xy plane provided, which isn't here, but we can just draw one. Indicate the direction of motion. So they're kind of asking us to do what we've done before, many times. So It might be good to go ahead and try and get a Cartesian equation. So, y equals 2t, x equals sine 3t. So we could solve for t in terms of x. It's going to be a little ugly. It's going to be inverse sine of both sides, right? And then divide by 3. So now y equals 2/3 inverse sine of x. That's a Cartesian equation. So it's an inverse sine curve. We can make a little table like we've done many times before to help us. We're going negative pi to pi. So you're asking yourself, this is the same thing as saying, well, inverse sine of negative pi. Like, when do you get negative pi as, well, we're going to plug negative pi up here. So the x sine of negative 3 pi is, you can just imagine the graph, sine curve. It's pi, it's 2 pi, it's negative 2 pi. It's going to be 0, right? 0 for that. And then 2 pi, negative 2 pi for the y coordinate. And then you do pi, sine of 3 pi is 0. You get 2 pi. Now the graph is going to be inverse sine curve. This is kind of annoying, but whatever, I'll try it. Okay. We can start with the sine curve, right? And this would be pi, this would be negative pi, 2 pi. And so what happens is, that's 1, negative 1. What happens is the graph gets flipped. Plus y equals x. So the graph looks like this. And it just keeps going. Now, we introduced the inverse sine, so it's not necessarily principal values like we've kind of always thought of on these inverse curves. So it's going to go from here, it's just showing you, we're going to go from negative 2 pi. Now, the graph, usually this is at pi, but now it's actually at 2 pi over 3 because of the extra 2/3 in front. And this would be usually 2 pi, but it's not going to be 4 pi over 3. And this is 0, and this would usually be negative pi, but it's negative 2 pi over 3. This would be negative 2 pi, this would be negative 4 pi over 3. We want to go all the way down to negative 2 pi and all the way up to positive 2 pi, so I think we've got to keep going. This would be, so this would be pi, 2 pi, 3 pi times 2/3, that's going to be 2 pi right there. And right here, this would be negative pi, 2 pi, 3 pi, but times 2/3 would be negative 2 pi. So it's this whole graph. It's kind of crazy. This whole thing. And this should be negative 1 to 1. So there you go. Crazy. All right. Sketch it. Indicate direction of motion. Well, this negative 2 pi, so this is 0, negative 2 pi. This is the initial point, right? And this up here, 0, 2 pi is the terminal point. So it's going this direction, right? Keeps going that way. Okay, so I guess that's A. Interesting. B says find the range of xt and the range of yt. So range is the possible output values for x. Now, you could tell here what are the possible values of x we get, -1 to 1. So I think, our range for x is between -1 and 1. And then our range for y, what are the possible y values we get? Well, they go from -2 pi to +2 pi. So I'm just basing this off the graph. But I mean, you could look at these yeah. So range depends on, domain, and we know that we're supposed to be using -pi to pi for t. Okay, C says find the smallest positive value of t for which the x coordinate of the particle is a local maximum. What is the speed of the particle this time? So we're looking for the first local max time-wise, or the smallest positive value of t. So first positive value of t, that you get a local max. Okay, well, for the x coordinate, so we're looking for a relative max of x. So we need to find the critical point. So we need to do x prime, which is also v sub x. And that would be 3 cosine 3t. And we're going to set equals 0 undefined. And so then cosine of 3t equals 0. And so then 3t equals pi over 2 plus pi k. And t equals pi over 6 plus pi over 3k. And so t equals pi over 6 plus another 2 pi over 6 is pi over 2 plus another 2 pi over 6. That's 3 pi over 6, 5 pi over 6. Also negative pi over 6, negative pi over 2, and negative 5 pi over 6. These are all the points possible, but we really only want the positive ones. And it says the smallest positive value for t. So it's got to, well, these aren't necessarily relative maxes. So we could do a line check real quick. We're only concerned with negative pi to positive pi. These are times. Okay, so we're going to test a value. Time equals 0. I don't know. So that's going to be positive, negative, positive, negative, negative, positive, negative. So decreasing, increasing, decreasing, increasing, decreasing, increasing, decreasing. So this is relative min, relative max, relative min, relative max, relative max, relative min. So we want the smallest t value gives you relative max. So that's that. It's t equals pi over 6. Okay, looks good. Part D's. Oh wait, hold on. Shoot, do we have to do something? What's the speed? Gotta find the speed still. Classic mistake. Find the speed here. So that's gonna be the square root of dx dt, which we just found was 3 cosine squared, and then dy dt is just 2. Now, this is going to be pi over 2. Cosine pi over 2 is 0. So this is going to be square root of 4. So it's actually going to be a really nice answer, too. Easy without a calculator. Right? There you go. 2. All right, part D says, is the distance traveled by the particle from negative pi to pi greater than 5 pi? Justify your answer. It's the distance traveled. Well, how do we find distance? Distance is this length, which is the integral of speed dt, which is going to be, so from negative pi to pi, it's going to be the square root of dx dt, which we just figured out was 3 cosine 3t squared plus dy dt, which was 2 squared dt. So this is how we would, usually calculate this. So it's going to be 9 cosine squared 3t plus 4. Now, I don't think I can do this by hand. So I'm going to go ahead and use a calculator at this point. So math 9, square root, 9 parentheses cosine 3x close squared close, and then plus 4 close comma x comma negative pi comma positive pi. Let's see if this works. Working on it. Wow. It's hard. Still going. There it is. 17.973426, and then it says, is it greater than 5 pi? That's a question. Well, what's 5 pi? 5 pi is 15.707963. So yes. Yes. And there's my answer. There's my justification. Okay, that's it.